This video is going to be about global warming and the energy balance of the Earth. So anytime we talk about global warming or climate change, we're always going to start with the concept of what's bringing about this problem, or what is causing the Earth to be warmer than it should be. The number one thing that determines our Earth's climate and our temperature of the Earth currently is carbon dioxide, or CO2. And we can see evidence of this if we look to our neighboring planets. So the Earth has an average temperature, which is really great for humans, of about 14 degrees Celsius. And we have a 0.4% atmospheric concentration of carbon dioxide and a little bit of water vapor too. Okay? If we look to our neighbor to the left, we see that Mars has no atmosphere. I should say it does have an atmosphere. It's just really not dense. So it doesn't have many gas particles at all. And it's much colder than the Earth. Negative 80 degrees Celsius to about negative 60 degrees Celsius on average. Versus our neighbor to the right here, Venus, has a very high carbon dioxide concentration, 96.5% carbon dioxide in its atmosphere. It's very dense and very thick, and it has an average temperature of 462 degrees Celsius. You might be thinking, Mr. Babcock, you're cheating. You're choosing a planet closer to the sun. Of course it's hotter. Actually, Venus is the hottest planet in our solar system, even though it's the second farthest planet from the sun, or second closest planet to the sun. So it's actually hotter than Mercury, which is closer to the sun. So carbon dioxide concentration does matter, and in Venus's case, it's so hot that it has rivers of molten lead on its surface, so it's hot thanks to carbon dioxide. So carbon dioxide is the number one determiner of our warmer than normal climate, but there are other gases which we can classify as greenhouse gases that you guys need to know about. So carbon dioxide's one, but we should also include methane and other nitrogen oxides are responsible for climate change and the Earth being warmer than it would be without those gases. However, the most abundant gases in our current atmosphere, oxygen, nitrogen, are the most abundant gases in our atmosphere. Those are not greenhouse gases. Okay? So the majority of our atmosphere is not a greenhouse gas, thank goodness, otherwise we'd be like Venus. But the small concentrations of greenhouse gases, as you'll see once we continue on a little bit further, are what help make Earth livable. And increasing our concentration of these gases will make Earth way too hot for us to live here. So we should really think about what we can do to limit the greenhouse gases in our atmosphere. So there are two factors which determine how much impact a greenhouse gas is going to have on our climate. And so the first factor that we need to think about is how well the gas absorbs infrared radiation. Okay? So the two number one absorbers of infrared radiation in our atmosphere right now are water vapor and carbon dioxide. Okay? And the major components of our atmosphere, such as nitrogen and oxygen, they do not absorb infrared, which makes them not greenhouse gases. Okay? So how well the gas absorbs infrared radiation? If it's better at absorbing infrared radiation, it's a better greenhouse gas. If it's unable to absorb infrared radiation, like nitrogen gas and oxygen gas, it's not a greenhouse gas. And the second factor has to do with the concentration of those gas particles in the atmosphere, which can be affected by the rate that we release that greenhouse gas into the atmosphere and the amount of time it stays in the atmosphere. So for example, carbon dioxide stays in the atmosphere for 30 to 90 years. So the carbon dioxide in our atmosphere currently If you produce carbon dioxide today, it would take about 30 years for photosynthesis and other processes to remove it. So that's something to think about. Now, I mentioned earlier that it's important that to be a greenhouse gas, that you're able to absorb infrared radiation. So why is that important? So let's think about the light that comes from the sun and the wavelengths that make up that light. So the light that comes from the sun is made up of ultraviolet radiation, it's made up of the visible spectrum, and it's made up of these wavelengths all the way down to the micrometer. But the majority of the light lies in this region here, where we have visible light and just barely infrared radiation and ultraviolet radiation. Okay? That light, if we draw this out, if this is the Earth, and I have fluffy clouds of greenhouse gases above my Earth, so that light comes in. I'm going to use blue because it's shorter wavelength. That light comes in from the sun, and it goes right through the greenhouse gases, because remember, they only are absorbed, they can only absorb the infrared radiation. Now, when that light is incident on the Earth, what happens is the Earth absorbs that radiation and it re-emits it. Only when it re-emits it, now it's longer wavelength radiation, okay? And this longer wavelength radiation can be absorbed by greenhouse gases. So if on the way back after being emitted or re-emitted by the Earth, that photon of infrared radiation is incident on a greenhouse gas, it'll be absorbed. And then once it's absorbed, one of two things will happen. Either it'll be re-emitted, it can be re-emitted in any direction, really. So some of it can be re-emitted into space, and some can be emitted back toward the Earth, okay? And it's these that are emitted back toward the Earth, this group here, that are responsible for warming our atmosphere, okay? Okay, so this radiation we have coming into the Earth, and some of it being absorbed by the Earth, and some of it being absorbed by greenhouse gases, gives the Earth the temperature that it has currently. And so all of these absorbed, re-emitted, and reflected energy gives us kind of a balance of energies. And this diagram here kind of shows where all of that energy goes to and comes from. And so this looks really, really complex, but I just want you to think about three things that kind of simplify what's happening. So light can do one of three things, okay? So it's always going to do one of these three things when it contacts an object. First thing it can do is it can be reflected, okay? And when it's reflected, there's no change in wavelength, just like we saw in our waves unit. Okay, so there's no change in wavelength. And so we can see this in the diagram, that light comes in and it's reflected by the Earth's surface here. And that light that's reflected by the Earth's surface, or the light that's reflected by the clouds, that just goes straight back into space because it cannot be absorbed by a greenhouse gas. Okay? So the light that's reflected by the Earth and our atmosphere and clouds is not causing any climate change or any warming of the Earth, because that light is reflected right back out into space because it doesn't have the same wavelength needed to be absorbed by greenhouse gases. The second thing that light can do when it contacts an object is it can be absorbed. Okay? When light is absorbed, it's taken into the material, and then when the material returns back to its original energy state, it's emitted at a larger wavelength. Okay? And so this light that comes in, I'm going to circle in green. So the light comes in, it's absorbed by the Earth's surface here. Okay? This light coming in that's absorbed by the Earth's surface, and this energy that's absorbed by the Earth's surface can then be radiated back here, and this energy that's radiated back is going to be radiated in the form of infrared radiation, and that's why it can be absorbed by greenhouse gases. Okay? When it's absorbed by some of the greenhouse gases, that means some of it can be emitted back toward the Earth's surface, and some of it can be emitted back toward space. The re-emission process can happen in any direction, and so it doesn't, just because it's absorbed doesn't necessarily mean it's emitted back toward the Earth's surface, but odds are that half of it will be, and half of it will be sent upwards. Okay, and the last thing light can do, which doesn't really have much to do with this energy diagram, is it can be transmitted. Okay, just like light going through air or glass or water, it's not absorbed, it's not reflected, it goes right through and propagates the electromagnetic wave through that substance. There's no energy transfer here, or no, this isn't not on the diagram. I've just included this because I wanted a complete list. Alright, that is it. That's it.